Let's take a look at a new kind of biomedical model here. Consider a patient who is being given morphine at a rate of 2.5 milligrams per hour, a continuous dose. Their body metabolizes the drug at a rate of 30% per hour. And what that means is the dosage is going to be constant, so we're always injecting the same amount at a certain rate, but the metabolism is actually more effective if there's lots of morphine in the system, and it takes out less if there's less in the system. And that's simply because that's the way the kidneys work. It works on a proportionality sense. What we can do is very easily turn this into a differential equation model, though. If we let m equal the amount in grams of morphine in the patient, then the rate of change of morphine in the patient is going to equal the rate at which it's coming in. That'll be a positive contributor to how much is in the patient's body. And then we can subtract the rate at which it's leaving the body, because that would be a net negative on the rate of change overall. Or you can talk about this being the net rate of change. And the nice thing about that kind of model is that some of these rates are actually given to us. Hey, we're injecting morphine at a rate of 2.5 milligrams per hour. So we'll put our units down here. And the rate out, we're metabolizing the drug at a rate of 30% per hour. So roughly speaking, after 1 hour, we'll lose 30% of the current amount. We can write that out as 0.3 times m. 30% of what we have, we're going to lose, and that's going to be our net negative effect there. And if you look at the units here, we've got 1 over hours, and the units of the morphine level itself are grams, and so, sorry, milligrams. And so everything's in milligrams per hour as we go through this. And that's it. So building up a model for what could initially look like a very complicated system turns out to be very straightforward. We have an amount in, and a rate in, keyword here is rate, that's in units of milligrams per unit time. And we have a rate out, which is 30% per some unit of time again. And when we multiply that by the amount, we get milligrams per hour, and we get, by combining those two, the net rate of change overall. Now from there we can find a general solution, because there are questions we like to ask that we need the solution for. So our differential equation is 2.5 minus 0.3 m is equal to our rate of change, and we separate, and we will integrate in a second. The only way to separate this really is to bring the entire thing, this entire right-hand side, down to the other side. And if we do that, we'll get 1 over 2.5 minus 0.3 m dm equals, well, if I bring the dt up, that's all there is on the other side. And we'll integrate both sides now. When we integrate the right side, let's do it because it's easy. We're going to get t plus a constant. The left-hand side's a little trickier. It's a ln, because it's just a linear function in the denominator there. But we have to be careful. The variable is m, and we have a negative 0.3 with that variable. So we'll have to divide by that. Again, remember you can always check these things. We could take the derivative with respect to m. If I differentiated ln of this, I get 1 over. But then I would get a times negative 0.3. We don't want that, so we have to divide by negative 0.3 when we do our integration step. But that's it. We've separated, we've integrated, and now our goal is to solve for m equals. So let's take a look at how we might accomplish that. Obviously bring the negative 0.3 up first. Maybe not obviously, but I think that's a good first step. So negative 0.3t minus 0.3c. Then exponentiate. We want to get into this m, so we need to get rid of the ln. So we'll exponentiate both sides. And when we do that, we will get rid of the ln on the left. E to the ln undoes itself. So all we have is 2.5 minus 0.3 m equals e to the negative 0.3 t. And because we're subtracting here in the exponent, we can multiply down in the bases. That's going to make it easier to make a nice new constant, e to the negative 0.3 c. We're now at a scenario we've seen before. What we're going to do now is we're going to invent a new variable, just because we don't really care what c is, and it's always going to appear in this form of e to the negative 0.3 c. So we're going to put that in here. And we also have these absolute values. So if this ended up being negative, we'd make a negative. If this ended up being positive, we'd make a positive. In the abstract, we can sort it out later on. Sorry, in practice, we can sort it out later on. The nice thing is it lets us keep moving with our solving. This whole term here, we'll bring it to the front, but we're calling it a, and e to the negative 0.3 t. And we're almost there. So we can bring, I think the most efficient thing is to bring this over to this side, that over to that side. So we get 2.5 minus a e to the negative 0.3 t equals 0.3 m's. And last but not least, we can solve for m. 1 over 0.3, 2.5 minus a e to the negative 0.3 t. All right, so that gets us a long way towards the solution there, which is nice. And we can talk about what the solutions might look like then. Let's actually take it one more step, though. What is this going to tell us about the long-run behavior? If our differential equation, let's look at that first, was 2.5 minus 0.3 m, and our solution was m equals 1 over 0.3, 2.5, I believe, sorry, go back one page here, 2.5 minus a, e to the negative 0.3 t. One of the things we'd be interested in is this dosing regimen's long-term effect. In the long run, how much morphine will the patient have in their body? Well, that sounds like a long-run question of a limit. The limit as t goes to infinity of m is going to equal what? Well, the 0.3 is going to be there, the 2.5 is going to be there, but what this exponential is going to do is, well, it's e to the negative something, t is getting bigger and bigger, that's going to converge to 0. And so what we get in the long run is 0.3 over 2.5 over 0.3 is approximately 8.33 milligrams. So in the long run, if we had a patient, regardless of what their initial value is, though we started off with, actually no, here we didn't even specify what the initial value was. If we talked about the morphine level against time, and we talked about 8.3 milligrams, that is where we would end up. So if we started at nothing, then in the long run we'd end up at 8.3. If we started halfway up, we'd end up converging towards 8.3. And let's say we were on a higher dosing regimen, we would have an exponential decay towards 8.3 again, because we'd have too high a level in the body and the metabolism would be too effective. We can see that 8.3 level, though, also as an equilibrium level, looking back at the differential equation. For the equilibrium levels, that would be an m that's constant, where the balance is, where there's a balance between the inflow of morphine from the dosing and the outflow from metabolism. If those are in balance, then the rate of change would be 0, which means that 0 would equal 2.5 minus 0.3 m. Bring that over. 0.3 m equals 2.5, or m equals, wait for it, 2.5 over 0.3, or again, 8.3 milligrams, 8.33 milligrams as the equilibrium level. There we go. And again, we could see that on the graph. If that's an equilibrium level, if we start there, we stay there. If we start there, we stay there. Rate of change is 0. All other starting points will end up converging towards that particular value, though. We can refine that sketch a little bit, add a few more details. But the key thing is, if this is time, and this is our morphine level in milligrams, and 8.33 is our equilibrium level, that would be our constant solution. If we started at that level, metabolism and dosing would balance and we wouldn't change. If we started lower, we'd go up. If we started here, we'd go up. And if we started above that level, we would have to decrease, because regardless of what A was in our equation, the long-term limit would have to be the single value 8.3. Everything converges back down to that in the long run.